deriving the long-run total cost function from a production function using Lagrange. This is a 4-step process, and step number 1 is to state that we want to minimize cost subject to a target level of production. So this is the total cost function. It's the sum of wage times labor plus rental cost times capital. That becomes our total cost. And we want to minimize that subject to the constraint here, the target level of output from this Cobb-Douglas style production function. So that's step number 1, to just state that. Step number 2 is to use the Lagrange method and solve for L and K. Step 3 is to plug those values that we solved for into the constraint and solve for L star and K star. These are the optimal levels of labor and capital. And final step is to replace L and K in the total cost function. This is the total cost function with the optimal levels of L and K, so that we get the long-run total cost function, which is now a function of our desired output level Q, the wage, and the rental cost. So, following the recipe, we say that we want to minimize total cost subject to the constraint, the target level of production. So we set up the Lagrange for this, like this. So here is the objective function, here is the constraint with the Lagrange multiplier. Then we take the first derivative of Lagrange function with respect to L, and then with respect to K. And these are first order conditions, means that they are equal to 0. And then we divide these two, because this is an equation system now. So we divide them by each other. We can see that I moved this to the other side. So we have the equal sign here now. So W divided by R. And then this whole expression divided by this whole expression. That's what we see here. And then things starts to cancel out. Like lambda cancels out. And if you look at K, for example, you can see that K is standalone here. Why is that? Well, I moved this K up here. Means that we would have K raised to the power of A. It flips signs when I move it up. Then this A and this A, they cancel out. So we're left with just K up raised to the power of 1. And that is just K. So that's why we see that here. Same story for L. So nothing strange about that. And then we solve this expression here for L and K. Now we are already finished with step number 2. So step number 3, then we substitute these values that we found into the constraint and solve for L. Then we get the optimal level of labor and capital. So I just flipped the production function around, the constraint function around here, so I've written it backwards. And then this K here, I substitute with this expression. So it goes here. And then we notice that we have L inside this parenthesis, which is raised to the power of 1 minus 1. If I move it outside, so then it's still raised to the power of 1 minus I, or alpha. And then we can see that this alpha and this alpha, they cancel out. So that's why L is standing standalone here. Final step is that I move this whole expression inside the parenthesis to the other side. If I do that, then these would flip signs, but they're still standing with the same sign here. So what I did here was that I flipped these instead. So you can see that here we have alpha R in the denominator. Here it's in the nominator instead. So that's why I kept the sign and flipped inside the parenthesis instead. For K, it's really just the same story all over again, following the same type of mathematical, what we could call that, mathematical steps, or, just doing it the same way as we did with L. Now we have these two expressions. This is L star and this is K star. This is the total cost function. So instead of L and K, we write this. And now we have the long run total cost function, which is now a function of W, R, and Q, the output level. It's not depending on L and K anymore. So this we now should look at a little bit more at using GeoGebra. So this is, these figures, when I work with microeconomics, I often feel that I can perhaps solve the equations if I'm lucky, but I don't understand what have I done? What does this equation mean? Well, I took this equation here, the long run total cost function, and then I entered into GeoGebra like this. So this is exactly the same, WQ, WQ, alpha R, and so on and so forth. And then I took all these parameters that we had, Q, alpha, W, R, and stated them here with sliders. So now I can change the level of output. See, 5.8, slide it down, 1.6. And when I do that, I can see that the graphs here, so the green one is the total cost function, and here is the isoquant, the production function, the constraint in blue here. Isoquant, maybe we should add a T there. So now I can change the wage if I want. So labor becomes more expensive. And then we see how this total cost that we want to minimize, that the tangent point moves to a point where there is less labor compared to when wage was cheaper, then it uses more labor. So we have labor on this axis and capital on this axis. I can, if I set them equal to each other, I have 1 and 1 now, normalized. I can change the weight, alpha. So alpha appears here. What does it do? Well, it changes the shape of the isoquant and moves the optimum when labor becomes more important. Or if it gives less weight to labor, then machinery becomes more important, or more optimal to use more machinery than labor. So this is a way, everyone can do this. It's just on homepage. You can go in and enter the values and equations and move things around and think about it. Think what it means to you. It helps to build intuition around otherwise rather abstract concepts, I think.